Hello, everybody. And today we want to talk about evaluating normality. Now, we're going to do it on a simplistic level. There are other levels that you can look at in my future videos in the advanced statistics playlist. Right now, I'm just looking at it as if we're beginning at a first level basic statistics 1 level. How can I judge if a data set is normal? The reason we want normal, remember, is so then we can model my distribution after the normal distribution and come up with easy and quick and efficient answers to any type of question like what is the probability less than, what is the probability more than, so on and so forth. But first, we need normality. Without normality, everything we've done in the normal section is violated. So how does one verify normality? Well, there are some quick, easy ways to do it. Let's show you the quick and easy ways. Go to data analysis in your Excel. If you don't have data analysis, you'll have to load it. Please watch Google videos on how to load the data analysis package in Excel. Descriptive statistics is what you want to click in data analysis, okay? And now we follow through. Input the range. So what this is going to do is it's going to give me the descriptive statistics breakdown of my data set, which in this case for question 1 are the annual taxes priced at the state median value. So what happens is these states, we found the median house value, and then we found the annual taxes in each state based on that median house value. And the question is, are annual taxes normally distributed? Well, to answer that question, the first thing I'm going to do is build a descriptive box. To do that, you load in the data, no headers, summary statistics, click, output range, put a spot where you definitely know bottom and to the right is going to be empty. So like right there. Let me retitle this for taxes so I know exactly which box this is. So the first thing I check, if somebody asks me, is my data normal? The first thing I check is, are the mean and median relatively close? That's the first thing I look. Are the mean and median relatively close? So when I look at the mean and the median house value, I don't see them as too close. They're off by 300, and that's pretty large in taxes. That's a difference, all right, of the mean and median by 300 in taxes. So my first check, which is a simple check of mean and median, they're not too close, which makes me think that we have some high-end taxes because the mean usually tends to go towards the high-end values. Second thing I note is the skewness. If the skewness is under 0.5, then that's good. See, the key is skewness is how skew left or skew right my distribution is from uniform. Sorry, wrong word. From symmetric. And if it's 1.55, there seems to be a positive skew. That kind of heads towards the fact that the mean is heading towards the higher end. So they're both heading towards a positive skew because of that. I want the skewness to be close to 0, okay? So the mean and median should be relatively close. They're not. The skewness should be close to 0, and it's not. The usual bound I put on this is 1/2, and this is clearly more than 1/2. All right, so what else can I do to check to see if there's normality? So far, I got 2 checks, and they both have failed. Well, you can draw the box plot. So we can highlight the data, and then we can insert recommended. Normally, it doesn't give me the box plot, so I got to go to all charts, box and whiskers. If you don't have the option of box and whiskers, you may have an older Excel, and that is the reason that you're having troubles. So I have the newest form of Excel. Let me click OK now on this box plot. And I notice right away something very important. I have outliers. First of all, there are 2 dots that Excel thinks are outliers. And so that would mean I probably should investigate that. That's also giving me the reason why I'm positively skewed. Notice, and let me put some numbers out here on the data labels. This is how you get the numbers. Click on the data labels, and the data labels come up. There's the median, there's the mean, but please notice the difference between quartile and minimum. That is about a 700 difference. Where up here, the difference is well over 2,000. That is a huge differential, and that's why I know there's a skew, okay? Because usually in a symmetric picture, these whiskers, as they're called, are roughly equal in distance. But then again, positive skew, look at the tail, going towards the positive infinity, going towards the positive end. Longer tail than this side. So that all three are leaning towards left skew, all three of these. And so that is why I'm not going to go any further. I'm going to definitely say we have a left skewed distribution, a positively skewed distribution. What does that mean? It's not normal. Now, could I look at these two outlier states? Maybe cut out the outlier states and then redo the algebra? I could. I could redo the analysis without the outliers and see what effect it has and see if maybe I could say everybody but these two states were outliers. All right? There are potentially two outliers here, 5244 and 7335. These two states seem to have more taxes than the rest of them, 7335 and 525252. This is why you put your data in order, so you're not scrambling looking for the two highest tax brackets based on median home values. Connecticut and New Jersey seem to be the outliers. We could, again, cut them out, redo the analysis without them, and see if we have a normal set, and we just say our distribution is normal based on all states but Connecticut and New Jersey. All right. Cool. So we know how to show it's not normal. And what it would mean here is this means I cannot do the simple questions of what is the probability in top 10% without being more careful. If you want those questions, I would order these in order and just cut out distributions from these. All right. So let's move on to our second example. Let's look at, are the number of patients per day at a local clinic normally distributed? Well, to answer this question, once again, we should run a descriptive analysis. So to run a descriptive analysis, you go data analysis, descriptive statistics, okay? Scan in the numbers you want to build the descriptive statistics on, just to count, not the day. Where you want to output it, make sure it is clear of anything, and it dumps. So this would be, again, patients, P-A-T-I-E-N-T-S, patients. So first thing I notice, the mean and the median are really close together. That is very, very important to me. If the mean number of patients, 79.8, and the median, 80 patients, are that close, that gives me hopes that there is really no outliers or any skew in one direction or the other. All right, so that's cool. Check 1 is good. Check 2, we look at the skewness number. Well, that skewness number is really close to 0. Remember, I said as long as we're close within the range of 1/2, we're good. You can look at your manual to decide how close your skewness needs to be for your application. So far, 2 checks. Remember, we looked at taxes, and the taxes were really far apart, and the skewness was way too positive for symmetry and for normality. Down here so far, we're looking good. Here's a check mark. Here's a check mark. I know these are not top-level proofs of normality. We do have some really cool proofs of normality in upper-level statistics. I'm trying to approach this from a very basic point of view, a quick check for normality. I can tell you right away, normality will not fit for taxes. But let's check it out for number of patients. So we highlight the data. This will be the number of patients per day over 30 days counted. So insert, recommended, go to all charts, go to box and whiskers, click OK. And we get this beautiful box plot, which I will now locate down here. And this is on patients. And I like to add the data labels so I know what the numbers are. So when I look at this box plot, and at any time, you should really pause and make sure you understand what each graph does. This is very important. These are kind of the quick proofs for normality. All right, so far for normality, for normal data, we have mean and median are really close. We have skewness is close to 0. Awesome. And now we have this. And what we're hoping for here is that, for the most part, there's equal spacing all around. 84 to 81, that's like a 3-digit jump. From 78 to 76, that's roughly a 3-digit jump because that's 78.75. So we're really looking at an equal spacing all the way around, which really gives me hope for normality. Again, these are not proofs. These are just ways of checking off boxes to say, hey, look, this looks good, this looks good, this looks good. How far do you need me to go to show you that it's normal? Well, if it's research, you might want to look into one of the normality tests we have in advanced research. If not, these are some cool indicators just to keep you in the right direction. All right, so what else do we have? Well, up in the taxes, I did add one more plot as I paused the screen for a moment. This plot is called the normal probability plot. Now in Excel, as of current Excel, they don't do this for you, so we have to build this. What we're hoping for in this NPP plot, the normal probability plot, we're hoping for a straight line. Any bend at all, any curve at all means we have a skew. And when we have this concave down, this bend down, that lines up with the positive skew that we have. So here, this clearly tells me we have an issue with linearity, even with the outliers taken out. Even if I take out the outliers, I still have this nice bend. This bend tells me I'm really looking at a non-normal data set. And if it's a non-normal data set, we should not be applying the normal distribution to it. So once again, taxes is not a normal data set, according to my data collecting. What about patience? All right, let's look at patience. So how does one build an NPP plot? That is a very good question. The way one builds an NPP plot is you have to build it yourself because Excel doesn't have it. Now, how does one build an NPP plot in Excel? You're going to need 3 columns of work. Well, you don't really need 3. I built it in 3 columns so I can see what's going on. Is first, we need to account for the numbers. And actually, I got to be careful. You first have to organize your data in order. So we have to organize our data in order. To do that, we do a sort filter command. I highlighted the headers so I can figure out exactly which one I wanted. Actually, I didn't highlight headers according to that. So I'm just going to use column H, smallest to largest. And you do want column to largest. All right. The reason being is I'm going to plot this one-on-one versus the normal distribution. If this data is roughly normal, then these values will line up to their associated Z values in a nice 1-to-1 positioning, which would create the perfect straight line in a graph. How does one do that? Well, first you got to enumerate the numbers in order. So after I have a couple down, Excel will fill in patterns. All of the things I'm doing here are cool little things one can do in Excel. All right? And what you got to do is you just got to learn how to do some of the basic sort and filtering commands. And now, what I'm going to teach you, or what I want you to see, is a nice little command for autofilling. Is once you have 2, you can say fill in the rest by double-clicking down, and it fills it in perfectly. Now, we need to know fractionally where this bar is broken. If we were thinking about the normal distribution and chopping it into 30 pieces, where would each piece be? The answer would be in n over n plus 1. What do I mean by that? I mean you're going to make the first chop out of the potential n plus 1 spots. So again, I keep looking. My n plus 1 would be 31. But your denominator will be 31 because it is n plus 1. Wherever n is, in this case is 30 data points, you want to use n plus 1 for the partitioning. Once you've done the 1, And of course, you've done the one by using this number. Now you're going to partition this whole thing up into slices. So this point, 84, is actually in the 96th slice of the distribution, according to my numbers. And if this was normal, that means this would line up beautifully with the probability with normal. And so what we're going to do now is we're going to run the norm S inverse on this probability and see what the Z value is for that. You see, what we're figuring out is we're figuring out the probability below each one of our numbers, and we're going to figure out the Z value for each one of our numbers. And we're going to see if the X value versus the Z value is in a nice one-to-one relationship. If they are, a straight line will happen. If they're not, a bend will happen. And that bend will let me know where the skew is. Again, in this case, this bend this direction meant we had a positive skew. So let's see what happens in this case. So what do we have? We have our X values. We position them on the normal distribution by doing the 1 through 30. We found that area underneath that slice by doing this. And that found the Z value for the area under the slice by using the norm as inverse. Now the question becomes, are the X values and their associated Z values, if we line them up on a normal distribution, are they in a nice one-to-one pattern? So we're going to insert. First, you got to highlight the two columns you're comparing. You got to insert. And usually, hello everybody. We had a quick little glitch there. So let's do this again to make sure you're with me. I'm sorry about that. So there was a little pause, a little interruption. We're back. We have the data highlighted because you want to compare these two. You insert, recommended, and the scatter plot comes up, and that's what you're looking at. The NPP is a scatter plot of your X versus your predicted Z values. If there is a chance for them to be normal, if there's a chance for your data set to be normal, this plot should be roughly linear. And by a quick check, it does look practically linear. And that's great news. So what I have here now is 4 quick checks. The mean and median are close. Check 1. The skewness is close to 0. Check 2. The spread in the box plot is pretty symmetric, pretty even. So that means check 3. And a little cooler check, if I took my data, sorted it, and plotted it against the normal plot and where the probability should line up, they're lining up in a pretty straight line, which means overall, we're looking at a pretty normally distributed data set. Are there more ways to check? Of course. Let me bring up my notes. You could have done the following. We've done the 1. We haven't drawn the histogram. You could check out the histogram. I mean, obviously, you could do that. You could check out the interquartile range. You could actually check out the range. And if you wanted to, you could look at the idea that if it's normal, think about what it meant to be normal. Within the first standard deviation, the plus or minus 1, you should see 68% of your data. So you could also check that for your data set. There are many, many quick checks using basic descriptive statistics like this to check if your data is normal. Yes, I do want you to understand there are advanced tests, but these are quick and these are good. I mean, right away, I could tell you this is not normal. All 4 of these fail. This, the patients have a really good chance to be normal. I have 4 good checks here, and I can continue on if you don't believe me. What that means, though, is if I found the number of patients per day at a clinic is to be normally distributed, that means I can now draw the normal distribution and answer simple questions of what is a busy day? You know, what's in the top 10% of busy days? What's a slow day? What's in the bottom 5% for a number of patients? All right, how many patients would it take to be a slow day? What's the probability we're going to see more than 89 patients today? What is the probability we're going to see less than 82 patients today? All these can be answered because we have that normality. And that is awesome to know. All right, guys, thank you for watching this video. Stay tuned for more.